Okay, so welcome everyone to the Online Risk Institute seminar series. Although we've got Silvia here today in person. Today we're going to have Dr. Silvia Tolo, who's going to give a talk about the current challenges and future solutions for systems safety analysis. And so, as always, our talk is going to be about 45 minutes, followed by some discussion questions for 15 minutes. And so I'm gonna, before we start, I'm gonna make some announcements. Okay, so this is a schedule for the next couple of weeks. Next week, we're going to have Dr. Christian Schilling. On the 13th of July at 2 p.m. He's going to give us a talk about gentle introduction to reachability analysis for dynamic systems. And the following week, we have Mr. David Ropek, who's going to give us a talk about risk communication. It's not just about the facts. So I know that everyone is probably familiar with Silvia, because she's a Risk Institute alumni. I'm going to give you a little bit of formal introduction. Dr. Silvia Tolo gained an M.Sc in Energy and Nuclear Engineering from the University of Bologna. So I'm just going to let someone in. And subsequently collaborated with Institute for Risk and Uncertainty at the University of Liverpool, where she was awarded a Ph.D. She is currently undertaking research within the Resilience Engineering Research Group at the University of Nottingham on the development of theoretical and computational tools for the efficient modeling of complex systems. Okay, so I'm going to just pass to the screen. So I have fancy slides here. So I'll just, yeah. You might use that.
All right, well, thanks for the introduction. First of all, thank you very much for having me. It's nice to be back in the windowless building. So what I want to present today and to discuss with you, as said before, is what we are at in terms of system safety and the tools that we use for the analysis and what we can do better. So let me start from the very beginning. And when I mean from the very beginning, I mean from the very beginning of system safety, because as a discipline, system safety in the shape that we know it, sorry, I'm just going to make people.
You're in charge now.
As I was saying, system safety as a discipline is fairly recent, meaning that was not really around in the shape we know it before the second half of the past century. Of course, there were systems before then, and most definitely there were safety issues with those systems. But the general approach was one of common sense. So the idea was to try to minimize the hazard in the design phase of the systems and then to fix the problems just as they came along. This in the aviation industry was known as the fly, fix, fly approach that, yes, is as terrifying as it sounds, because it consisted in having an aircraft flying a circuit and then just fix the problem anytime that the aircraft crashed, till reaching the ideal design, meaning the design that didn't crash for a while. Of course, this kind of approach was possible only in a world of really low and slow aircrafts and became rapidly unfeasible, not only in the aviation industry, but across all engineering applications. In particular, after the Second World War, when a lot of engineering systems were shifting from application and merely to the military sector to also the civil sector. We're speaking about the 50s of the past century, so when the debate about the safety of nuclear power started, or when the chemical industry was starting to deal with increasingly bigger size of plants and, of course, increasingly dangerous chemicals as well. And also when the aviation industry was trying to convince a skeptical public to fly. And of course, maybe the fly, fix, fly approach was not the best option to convince people to step on an airplane. But of course, we are also speaking about the beginning of the Cold War and then the race to the best and the newer weapons. And in fact, in the weapon industry, for the first time, the need for a more organized approach to system safety was identified. When indeed the Atlas and Titan intercontinental ballistic missiles were being developed in the US in the 50s, there was not, system safety was not regarded as a standalone responsibility or as a discipline on its own. On the contrary, again, the approach was pretty much, again, common sense. So each designer or engineer was considered responsible of the reliability or safety of the components, subsystems, or section of the systems that they were developing. So of course, this approach turned out not to be great. And in fact, it's enough to think that of the 71 missiles that were deployed, four exploded in their own silos within 18 months from becoming operational. And in general, the missiles had a very extreme launch success rate. So it became increasingly evident that safety was an issue to be dealt with on the system level and not property of the individual parts of the system. So it became evident also that like a new kind of approach, new tools were needed to face this problem. And in fact, it is in the 40s that the roots of the problem become, I mean, like the need for a new approach to system safety started to be there because of the increasing complexity of the systems. And it is in the 50s that this was recognized. Finally, it's in the 60s that we start seeing the first real efforts and the first tools. In fact, it is, I think in 68 that George Miller, I think is who is referred generally as the father of the space shuttle, defined what it was at the time the newborn discipline as organized common sense. So almost suggesting that common sense was not enough anymore. And since then, the principle of system safety has spread across all possible engineering sectors, so from the weapon industry to the nuclear sector to the space program as well. In fact, it's in 1967, for example, after the fire of the Apollo 1, the NASA commissioned the implementation of guidelines for that will become the standard for civil space flight. And in fact, these kind of efforts in the 60s are even more evident if we look at the tools, the analysis tools that were developed. And in particular, if we focus on the more quantitative techniques, we can recognize what are still today the industry standards. So in the 60s, were developed the reliability block diagrams. The fault trees were developed in 1962 at the Bell Telephone Laboratories in the context of the Minuteman missile program. So again, weapons. Forward event trees, we'll have to wait another decade. They were in fact produced in 1974 in the context of a nuclear safety study. So actually they were produced in order to deal with the excessive size of the fault trees for nuclear application. Funny enough, that's still an issue that affects the nuclear research and nuclear industry. Of course, since then, the discipline has grown to become what we know today with thousands of publications across all possible engineering sectors. And in particular, if we look at the number of publication on the topic of system safety, we can see that the growth of the number of publications has been exponential since the 90s. However, when we look at the publication on the topic of system safety, but using the techniques, the traditional techniques that we mentioned before, such as reliability, block diagrams, fault trees, event trees, and a combination of the two, the data tell a slightly different story. In fact, there is a sort of growth, but it's definitely not exponential. Things change when we start widening our research and considering other kind of techniques, like Bayesian network, dynamic fault tree, Petri net, and Markov models. Most of these techniques, apart from the dynamic fault trees, were not developed strictly in the context of safety analysis. They are kind of adopted from, if you want, other kind of research fields. But what they have in common is the modeling flexibility that they offer, and then the capability to capture complex features of the system, capabilities that is not proper of the traditional techniques. Now, of course, this is only indicative, and of course, this refers probably more to what is the academic reality rather than the industry, where instead fault trees and event trees, as I said before, are still the industry standards, in particular for large-scale systems. But I still think that these data suggest that the scientific community has been looking for new tools somewhere else from what are the traditional techniques for system safety analysis. And I do believe this to be connected to the challenges that system safety analysis brings to the table. And for example, the challenges that we have with new systems. I'm sure that pretty much everybody remembers the issues related to the Boeing 737 MAX that resulted in the aircraft to be grounded for 20 months in March 2019, after being involved in 2 major accidents in which, unfortunately, over 300 people lost their life. So the investigation after the accidents revealed that the issues seem to have been with the MCAS system, the maneuvering characteristics augmentation systems, which is a flight stabilizer software system, which was introduced in the final stage of the design of the aircraft in order to correct the tendency of the nose of the aircraft to pitch upward during stunt maneuvers. So the idea of the MCAS and of the system was basically to correct the inclination of the plane on the basis of the reading of an angle of attack sensor located at on the nose of the aircraft. And apparently both the accidents were triggered by a false reading of such sensors. In the first case, so in the first accident, it seems that the crew was not able to recover the control of the aircraft. For the second accident instead, it seems that they obtained in the end the manual control of the aircraft, but unfortunately, it was too late to make a difference. And looking into the safety analysis carried out by Boeing and submitted to FAA, the Federal Aviation Administration, so the regulator, so the safety analysis approved by the regulator, apparently the pilot response to an unexpected, so an unwanted activation of the MCAS system was of only 4 seconds. So beyond what are can be the deficiencies of the design or the the responsibility for the accidents, I still think that this example is quite significant to highlight some challenges that the new kind of systems are bringing to the table when we're speaking about safety analysis, which are, first of all, the large adoption of automation and control technology, which introduce a dense network of dependencies among the components, but also that makes the system intrinsically dynamic. And in particular, when we think about the interaction between the humans and the machines itself. What I mean is that if we want to understand really the behavior of the system, and if we want to estimate reasonably its safety, we need to be able to characterize the response of the system to a failure and then the evolution of the failure in time. So we need to be able to depict the dependencies and the dynamic behavior of the systems, and also, of course, of the human-machine interaction. And this is all the more true when we think of the shift that is being promoted in the last decade, maybe, towards a more resilience-based engineering design rather than merely reliability-based. But the problems and the challenges that we have with safety analysis do not lie only with new systems, but also with actually those systems that are not getting any younger. And I'm sure, like, we're all aware of this, but if we look at the global nuclear fleet, more than 2/3 of the reactors currently operational are over 30 years old, and 30 years over an expected or designed initial operational life of 40 years. More than 100 reactors are already being granted life extension licenses, and we know the more are coming. But this means that what we are doing is to push these systems to work, to force this system to work over beyond their designed operational life. So we are kind of pushing them in an unknown territory. Since the 90s, the International Atomic Energy has raised concerns about the consequences of aging nuclear systems in terms of safety, and in particular in terms of degradation. So the main worry is that the degradation of the system can trigger the loss of key functionality that can in turn impair the protection provided by the defense in depth that is at the very core of nuclear safety. So we have challenges in terms of new systems. We have challenges in terms of all systems. So new problems with new system, new problems with old system. But we also have just the good old problems that are generally related to our ability to depict reality and how we treat uncertainty, meaning that, of course, as always, we do not have the full picture of a system, and we do not have often the tools to represent exactly even what we see or what we know. So the solution for this is generally adopting a conservative approach, introducing strong assumptions. But the problem with this solution is that in a big project or in a system, conservative assumption or conservative approach doesn't add up, sometimes multiplies. What I mean is, if we have 10 engineers working on a system and everybody introduce assumptions and a conservative approach in terms of making up for the lack of information, of the right tools, what we end up in the end for the entire system is an unknown level of conservatism. Now, this may result in over-conservatism and over-engineering, which in the best case scenario may have only economical consequences. So it means that we are putting, for example, on the market a product that is not as competitive as it could be. And this is generally what is often discussed in the nuclear sector, and is one of the main arguments in favor of the small modular reactors. But on the other hand, a known level of conservatism means also that we could be less conservative and less safe than what we thought. Or even you can have both, believe it or not. In fact, in 2020, several international agencies carried out investigations, of course, about the NCAS system on the 737 MAX. And I think it was the European agency and more concluded that at the end of the day, the MCAS system on the 737 MAX wasn't really needed. So in that case, if that's true, what we have here is a case of over-engineering that ended up in a safety disaster. So the challenges that we have in safety analysis do not really lie with the systems itself, because we have challenges with new systems, we saw with the old system, but they lie with the tools that we use for the analysis itself. What I mean is that traditional methodologies, as the one that we mentioned before, are just not good enough in the sense that they are not able, for example, they are based on the assumption of independence between the components. This means that they are not able to capture the dependency between the components, but this also means the dynamic interaction between the components, often the human technology interface, and are also very limited in terms of maintenance models. So we're seeing more and more efforts in terms of maintenance strategies, condition maintenance. We have a lot of new solutions for maintenance. But if you're familiar with fault trees, you know that the models that we apply are basically three. We have three formulas to represent the possible maintenance and failure models. That is, it breaks and I can't fix it, it breaks and I can fix it when it breaks, or I can inspect it and eventually fix it, and that's it. On the other hand, another assumption is the constancy of the failure and repair rates. But of course, when we are speaking about aging systems, so the deterioration, this is just unrealistic. This is just unrealistic. And finally, as we said before, when we do not have the right tools, when we are not able to capture the reality of our system, what we generally do is to introduce our conservative assumptions. They come at a cost, or better, they come at a risk, as we saw before. On the other hand, we do have sexier and better solutions in terms of modeling flexibility. We have, for example, simulation-based techniques. The problem with this, though, is that when we are talking about large-scale systems, they become rapidly computationally infeasible. And I'm speaking about not even a jet engine, but let's think about a nuclear power plant. How do you build and run a petri net of a nuclear power plant? It's just not feasible. And this explains why these techniques have been very successful, in particular in academic study or for smaller systems, but not as much for large scale real world systems. So what can we do then better in comparison to what we have? Of course, everybody has a different recipe for the same dish. So what I would like to discuss today is what we've been working at for the past year and a half. And so our personal recipe in terms, I'm speaking, of course, of the research group I'm working with at the University of Nottingham. So when we started, we put down some objective and some property that we wanted for our framework, our simulation framework, and our methodology. First of all, we wanted to maintain the familiarity of the modeling language. We wanted to maintain the fault tree and event tree language, and this for different reasons. First of all, because it is still the language of system safety in industry. If you're discussing with the regulator the safety of a nuclear power plant, you bring fault trace. So it's still the language that is shared between regulators, analysts, and engineers, etc. But also at the end of the day, they are very limited, that's true. But also they kind of brought us here in the sense it's not all, they've been working quite well so far. So we don't need to reinvent the wheel. We can use the things that work. And the main thing that works is they are computational feasible, meaning that we are able to run it for a very large scale system. And we've been doing that for a few decades now. On the other hand, we wanted to overcome the main drawbacks of the approach. So we want to be able to include in the modeling component dependencies. We want to be able to depict dynamic features and the aging of components, so the degradation, so non-constant failure and repair rates. And we want to be able also to put in all the fancy complex maintenance strategies that we can think of. The main objective or the hope is to increase the analysis accuracy, but at the same time to maintain the computational feasibility of the analysis. Of course, this is all very nice, but how do we plan and how are we doing this? Well, the idea is that of adopting an umbrella methodology, meaning that we want to use a series of techniques, not just one, integrated into one framework. If you want, the idea is pretty much that of a magnifying glass approach. So let's say we have our system, and for some parts of these systems, the traditional assumption, again, costs and failure rates or independent components may not be realistic at all. And for this section of the system, we want to be able to identify this section and model this section with techniques that allow us, with our magnifying glass, with techniques that allow us to depict more realistically that those aspects and those interactions in the system. And for this, we are using pattern nets or Markov model. Then we would collect the information that we obtain from this sort of sub-analysis in terms of probabilistic information that we can reinsert in the fault tree through the use of binary decision diagrams and then carrying out the analysis. Probably not everybody's familiar with binary decision diagrams, but the only thing that we really need to know is that is a technique to resolve fault trees, and it's been around for I don't know, 50 years or so. So also that is well rooted in practice. So let's look at the methodology now, step by step instead. As I say at the beginning, we want to maintain the modeling language of fault trees and event trees. So in inputs, we do have pretty much what you would expect to see in a fault tree analysis. So we have the structure of the different fault trees for different subsystems. Then we have an event tree that specify how the combination of failures of the different subsystems results in some consequences. That we have a component file in which we specify how the components fail. And finally, which is different from traditional fault trees, softwares, or analysis, we do have a dependency file, but if you want, maybe we should call it something different, more like a complex feature file in which we specify the different aspects of the system for which we want to use our magnifying glass, for which we want to have a higher degree of accuracy in the modeling. So given the inputs, the first step is to consist in calculating the reliability information for the independent components. So if the component is assumed to have a constant failure rate, which in some cases it could be reasonable. If we have a sensor and we change the sensor every 3 months, why not? We could say that the component is, we can say that the component has a constant failure rate. If instead the component is subject to aging and we want to represent that, we can use battery net to represent that. Or if that is subject to a different maintenance strategies, we can represent again that with Markov models or battery net. In any case, at the end of the first step, we collect the information about the reliability of the component and we store it for being processed in following phases of the methodology. The second step consists in identifying independent fault trees. So, of course, a fault tree is independent from the other fault trees if the components in that fault trees are, first of all, only belong to that fault trees and not appear in other fault trees, but also are independent from the components in other fault trees. If that's the case, we don't need to do anything. We can just skip this step and proceed to the next one. In case instead two fault trees are dependent, we'll have to merge the two fault trees and compute them, process them together. The third step consists in the identification of the dependency models within the fault tree. With the dependency models, what we mean is the smallest independent section of a fault tree model that encloses the components dependent from each other. We will use two different definitions. Let's say we do have a dependency group. The dependency group is a closed set of dependent components. Components that are dependent from each other, and these are closed sets, so they are not dependent from any other component that is not in the set. Instead, a dependency model is a section of a fault tree that encloses those components, but not only those components, you can have also independent components, but definitely includes all those components. Once we have identified the dependency models of interest, we can extract them from the fault tree and we can process them separately. Once we've done that, we can reintroduce the reliability information regarding these sections of the fault tree in the overall fault tree framework, and computing all the fault trees, the independent fault trees that we identify in step 2. And then finally, we can solve the event tree and calculate the frequency of the consequences that we are interested in. I do not expect this to be very clear, so I think the best thing that we can do is to have a look to a very simple case study and go through the solution together. So on the left-hand side of the slide, you can see a simplified industrial cooling system for which we want to carry the safety analysis considering a 20 years life cycle. And of course, to demonstrate the methodology, we have introduced a few complex features. So we have aging components in the system, we have complex maintenance strategies, and we have component dependencies. The overall system can be split into 4 subsystems. So we have a primary coolant system, first of all. If this fails, the detection system is supposed to, well, the detection system is supposed to reveal the failure of the primary coolant system, and then to trigger the activation of the secondary coolant system and the fan or secondary air coolant system. If both these 2 secondary systems, the secondary coolant system and the fan system, work, we have no loss. So there is no loss of cooling. If only one of the 2 works, we have a partial loss of cooling. If both fail, or if the detection system fails to activate them, then we have the total loss of cooling. Now, looking at the structure of the subsystem one by one. So the primary cooling subsystem consists of 4 components. So we have a tank containing obviously the coolant, and then we have an heat exchanger HX1, and then we have 2 circulation pumps, P1 and P2, that work in parallel. Now, what we are assuming here is that if one of the pumps fail, the other pump is still able to guarantee the correct circulation of coolant. So if one of the 2 pumps fail, the system is still working correctly. However, if one of the pumps fails, it's putting an increased load on the second pumps, on the second pump, which means is increasing the failure rate or the failure probability of the second pump and vice versa. So P1 and P2 are dependent, stochastically dependent from each other, because the failure of one changes the probability of the failure of the second. And we are representing this with a Markov model, as you can see in the picture. The secondary water cooling system is pretty similar. So again, we have a tank and we have an heat exchanger. This time we have only one circulation pump, P3, which is connected to a valve V1. And we also have a relay that under the request of the detection system closes in order to activate the secondary water cooling system. What we are assuming in this case is that the relay is an aging component, so as a non-constant failure and repair rate. We are representing this with a pattern net, as you can see. So we are assuming that the failure is distributed as a variable distribution, while the repair time is log normally distributed. The detection system, so the third subsystem we're looking at, consists of three components. So we have a programmable unit, we have a computer that processes the information coming from two sensors, S1 and S2, working in parallel. Also in this case, we need just one of the two sensors to work for the detection system to be successful. However, what we are assuming here is that a calibration failure may happen, hindering the correct working of the sensors due to a common cause failure. And again, we are representing this with a pattern net, as is in the picture. Again, as for the BDD, even if with the pattern net, even if we are not familiar with it, it's not essential. The only thing that is important is to know that they are like extremely flexible and simulation based. So they allow us to represent in details the dynamic behavior of systems. Finally, the secondary air cooling system has only three components. We have a fan, we have a motor, and we have the same relay that we had before for the secondary water cooling system. So of course, you remember the hypothesis for the relay, which is an aging component, so as non-constant failure repair rates. But so we are not going to look at that again. But the other hypothesis that we are introducing here is that there is a complex maintenance strategy in place for the motor. So we are assuming that there is a condition monitoring system in place, so that if the motor degrades, we are able to bring it back to the initial condition, replacing the bearings, if this is detected through the condition monitoring system. Otherwise, if it fails, we'll have to replace the entire motor. And once again, we represent this with a pattern net model. So this is the case study. Now we can go to the solution progressively. Okay. As we say before, first step is the calculation of the independent component reliability. On the left-hand side, you can see the input file for the case study. So, for example, HX1, which is the heat exchanger for the primary cooling system, is characterized by a constant failure and repair rate. So in this case, the assumptions are traditional assumptions. So we can just use the adequate model among the three models that are proper of water analysis. So in this case, we have a repair rate, but an inspection rate. So we know it's corrective maintenance. We just applied the right formula and we calculate the unavailability and the failure frequency of the component and store the information. Things are slightly different instead. For other components, for example, let's remember the relay is characterized by a non-constant failure rate. The failure time is a very good distribution, and the repair time is log normally distributed. So we represent this with a pattern net, as we said before. In this case, the pattern net is automatically generated, but this is not particularly important for this demonstration. So we have a pattern net, and what we do is run the pattern net to convergence, calculate on that basis the unavailability and failure frequency of the system, store the information. And we do pretty much the same thing with the motor. We did have a user-defined pattern net model in input that was representing the condition monitoring in place. So again, we run the pattern net to convergence, we collect the probabilistic information that we are interested in, and we store the information. So at the end of step one, what we have is the unavailability and failure frequency for each independent component. The second step, if you remember, was to identify the independent fault trace. And again, if you remember well, we did have a shared component. We have the component R, the relay, which is part of both the fault tree of the secondary water cooling system and the secondary air cooling system, or the fan cooling system. Of course, it's probably not the best way to build the fault tree, but for the objective of this demonstration, we'll do. So what we need to do in this case, we have a component that is repeated in both fault trees. So we need to merge the two fault trees together and treat it as one fault tree. Why do we need to do this? Because if we don't, and we consider the two fault trees separately, what we are actually saying to the model is that we have two different components, both called R, and both are relay. And this introduces actually a degree of redundancy that is actually not in the system, is not realistic. So we need to merge it and treat it as one, so that we know that the R component is just the same component. For the other two fault trees, for the detection system and the primary cooling system, we have no issues. They are already independent, and we don't need to do any kind of manipulation. In the step three is the dependency model identification, if I'm not wrong. So in this case, like for example, we do have dependent components. We say in the primary cooling system, P1 and P2, and in the detection system, S1 and S2. So for the primary cooling system, we say that the dependency model is the smallest section of the fault tree that encloses all the components belonging to a dependency group. And we know that P1 and P2 are a dependency group because they are dependent from each other. So in this case, very conveniently, the section, and so the dependency model is just the gate under which P1 and P2 sits. So we can extract this gate and just in a second time, we will be able to reintroduce this information in the overall main fault tree framework as a basic event with an equivalent reliability information in comparison to the dependency model. Same thing for S1, S2. Again, very conveniently, they sit under the same gate in this case. So we can just extract the gate under which they sit and treat this as a dependency module. So extract it, we will work on it, and then we will bring back the information into the main fault tree. So now we have identified the two dependency models that we have, and we can work on that now. So the dependency module are connected. The first one that we extracted from the primary fault tree is connected to the dependency group consisting of P1 and P2. We already know that we are representing a dependency between the two as a Markov model. So we can run the Markov model, or in this case, the steady state solution was adopted. And we can calculate the joint probability value, meaning the probability associated with each possible combination of the states of the two components. So we have the probability of the two components to fail, the probability of the two components to work, and so on. Once we have this information, we can use this probabilistic information to compute the fault tree through the use of binary decision diagrams. Again, I'm sure that not everybody's familiar with binary decision diagrams, but are a technique that is used to for the computation of fault tree, for the efficient computation of fault tree. Of course, in this case, what we are doing is introducing dependency in the binary decision diagrams, because we do not have marginal probabilities, we have joint probabilities. And of course, there are no algorithms out there to compute BDDs with dependencies, not that I'm aware of. So we had to put together our own algorithms for the computation of BDDs with dependencies. Unfortunately, that's beyond the intention of this presentation, but if you want any details, I'm super happy to talk about it. So once we introduce this information, probabilistic information in the BDD, we can solve the fault tree with dependencies. So we get the probability of the top event of the dependency model. And we do the same thing with S1, S2. This time, instead of the Markov model, our magnifying glass is a Petri net instead. So we run the user-defined Petri net. We get the joint probability values for each possible combination of the states of the two sensors, reintroduce the information in the BDD, and then calculate the probability associated with the dependency model 2. So in step 5 now, what we have is traditional fault trees, because the information that we calculated for the individual dependency model can be then reintroduced in the main fault tree framework as a basic event. Of course, the probability of that basic event is equivalent to the probability of that we calculated with the techniques that we showed before. So it's taking into account the dynamic interaction, for example, between P1 and P2, or the common cause failure and the dependency between S1 and S2. But it's still representable now as complex basic events that just we pop in the framework of the fault tree. And now we can just carry out the computation of the fault tree with whatever solution you want to adopt with traditional algorithms. Just to specify, regarding the two fault trees that we merged for the secondary water and air cooling systems, of course, if you remember how the event tree is structured, we need to know the probability not only of both systems to fail, but also of both systems to work, or one to fail and one to work. So we will have to analyze actually 3 fault trees. So we'll have to merge the 2 fault trees in input, or also the first fault tree in input with the not second fault tree, etc., etc. But at the end of the day, again, what we obtain is the calculation of the top event probability for each of the fault trees that we have identified as independent. And once we have this information, we can, of course, calculate the event tree. Because we do have a dependency between the fault tree associated with the fan system and with the secondary system, things are slightly different than from a traditional event tree, meaning that we do have a dependency. So we can use either conditional probability or joint probability. But in any case, as you can see, for example, for the calculation of the frequency of no coolant loss, we of course calculated the frequency of the primary coolant to fail, and then we have the probability of the detection system not to fail, and then we have the probability, the joint probability, because they are dependent, of the 2 secondary subsystems not to fail. We did calculate, we don't need to reproduce all 4 merged fault trees because of probability rules. We can just compute 3 of the merged 4 trees, and then we can calculate with a minimum joint probability manipulation the missing joint probability information, like in this case we did for the partial loss one. So we carried out this analysis, and what we have in the end is the results that we were looking for. So the frequency of the 3 possible degree or loss of cooling that we have. Okay, I hope that that was vaguely clear, or at least it gave like a vague idea of what we've been working on. But just to sum up, system safety as a discipline was born to tackle the challenges that the increasing complexity of engineering systems, and in particular their application to civil sectors, brought to light. And today we do have new challenges to a certain extent due to the new design of systems, like the heavy use of automation and control, due to the shifting to resilience engineering, but also due to the need for extending the operational life of some systems, like for the nuclear fleet. So we do have aging systems that we are just not ready to throw away. Traditional system safety techniques have lots of strength points, but at the same time are quite limited in representing aspects such as the dependencies between components and the dynamic features, or the aging of components. And this sometimes it just not enough to give a realistic representation of the systems. On the other hand, we do have simulation-based techniques, but they are very expensive and they are infeasible for large-scale systems. So what we propose here is it's an umbrella methodology that integrates the point of strengths of the two, so the computational feasibility and familiar language of fault tree and event tree and PDDs, but also the flexibility modeling of Markov models and Petrinet. And if you are interested in knowing anything else, don't hesitate to get in touch. Thank you.
Thank you. So thank you very much, Silvia, for a very interesting talk. I think we've got a little bit of time for some questions or comments if you've got in the audience. Do you have some?
Oh, I think that was an old question.
Yeah.
I'm not sure.
Maybe Peter, do you? Sorry, we haven't come back to your comment in the chat.
Hi there. Don't worry about it. It was I was referring to this very nice diagram of the umbrella approach. I thought Silvia was going to dedicate one slide to it, and and she was not pointing to components, but then this highlighting sequence appeared, so it kind of addressed what I said there. Can I follow on with a question and a comment then, please, if that's okay?
Can you go quick? Yeah.
Good job, Silvia.
Yeah.
Okay, so first of all, very interesting. When you said I know all of you are familiar with this BDD, I was like, yeah, no, not all of us. But anyway, do you see this? So first of all, where do you stand on digital twins? In that regard of system safety, because these guys are nightmarish to analyze the safety of, I think. And do you see your approach being applied to a multi-scale kind of scenario where you have the motor in your use case, for example, being disassembled, quote unquote, into stator and rotor and windings and so on for a fault tree, but then you zoom out and you embed that motor into a larger system, doing the umbrella approach again and so on? Any thoughts on that? I mean, I hope
so I think actually you're referring to like a couple of ideas that we are working on them. Oh my God, this looks
I know.
or a couple of ideas. So what we are working at the minute is in sort of two directions that I'm quite excited about. One is a sort of nested approach in which we are I'm not sure I'm replying to your question. You can tell me at the end. What we're doing is slicing up the dependencies, because, for example, one of the problems with this, with what I showed today, is that sometimes the dependency, most of the time, the dependencies are not between two components, are between two subsystems, and each subsystem has 10 components. So what do? Do you create a Petri net with 100 components that are dependent from each other, even if it's the subsystems? So what we're trying to do instead is to kind of have a Petri net, fault tree Petri net approach. So a layered one in which we represent the probability of the subsystem with the fault tree, and then we use this as an input for a Petri net, so that becomes the input for the fault tree. Regarding the more than the digital twin, actually, I'm also trying to partly go back to something that I worked a bit when I was in Liverpool. Yeah. That is, I would like to work on coupling this kind of framework with also physical models. So we do have the probabilistic setting of the system that tells us this component may have failed and what happens, and then we connect that through at the Petri net level. I think it would be the only really option to the, for example, a core model of a reaction, and we are trying to start looking into that as well. But in that case, the strength of the framework would be that there is already a sort of connector there, that is the Petri net, so we can use fault tree, Petri net, physical model, and then going back. But this is all at the very beginning. We're starting looking at that just now, really.
Okay. So your physical model doesn't come into computing the failure rates. Is that right?
What I mean for a physical model, I mean, for example, if you have okay, let's say that you have exactly the model that we were talking about before. So we know, for example, that the secondary system fails with a certain probability. So what is actually the consequence of the loss of failure in the cooling? What is the probability that, for example, the nuclear fuel gets damaged? And you can do that only with a physical model, like a core model of neutral.
Okay. But isn't that makes sense? But isn't it like a two-layer physical modeling approach? One to compute the failure probability of whatever component you have,
yeah.
And then two to compute the consequence of that component failing, or that's not how it works.
Yeah, no, I think I don't see that. This Zoom is like so weird. I wouldn't say that like it is too physical. Yeah, it is. It is. But like I generally, in my mind, at least in terms of terminology, when I speak about physical, I speak about the physical process within the system. So, for example, what's happening in the fuel. While when I speak about any technological aspects, so a component that works or doesn't work, I don't really refer to that as physical, but you're right. It's absolutely two aspects of a physical process, of course.
Right. I mean, because going back and kind of closing the loop on digital twins, you can say something like a component fails. Well, a component in your fault tree fails because it is actually a collection of smaller components. So the motor is not just one circle, right? It fails because, I don't know, the bearing has run out of lubricant. How quickly does it consume that lubricant? That's a physical model, right?
Yeah.
Or there has been a surge in the electric net. What caused that surge? I mean, I have about like 4 or 5 questions. I'm not going to swamp you with these, but I'll probably mail you. Thanks.
Oh, where are you located these days?
I'm back in Bulgaria.
All right.
Yeah.
Well, if you ever come like to the UK, maybe we can discuss that as well.
I was in the UK in May, end of May, and I was going to come in August, but it turns out tickets are killers. So not going to come in August.
But yeah, email me. It would be very nice to have a
Yes,
chat.
I will. Yeah, very interesting. Very interesting. Thanks.
Great. Thank you, Peter. We've got someone raised hands, Roberto.
Hello. Yeah. Hi, Silvia. How are you? So just I arrived a bit late, so I'm sorry about that. Maybe I didn't see the full presentation, and maybe you talked about this already. I was actually curious. I mean, you have a very sophisticated modeling approach, but I was trying to understand where the data comes in. I mean, and what kind of data do you need to kind of implement this type of approach in practice? I mean.
So the data that you need is the one that you have for fault-free. So you generally have the rate of the failure rate and the repair rate. Now, the problem is if you trust those rates or you don't trust those rates. If you don't, you do need to do your research and see like how it fails. If it's a non-constant failure rate, you will have to find the distribution for the probability of failure or the probability of repair. So that's one of the aspects that you can specify differently from a fault tree analysis. The other aspects are related more to how the components interact. So for example, in that example, if you want to represent the dependency between P1 and P2, you need to know what is the probability of failure of P2 under the increased load in case of P1 not working. But in other cases, the information that you need is not even experimental. Like in some cases, what you need to put together is just quite Boolean model, if you want, in the sense that sometimes you have call standby or worm standby, you have some sort of redundancy in which you say, I'm going to use this one and this second train or the second component is being used if this doesn't work. But then the two can't be in maintenance together. So in this case, what it is not really experimental data that you need. It's just the knowledge on how the system works and how you're treating maintenance. If that replies.
Yeah, it's very clear. So you're kind of embedding together like statistical information on the reliability of the components in the system and kind of engineering knowledge on how the system works, and this goes together.
We gave this we gave like a similar talk to more industry focused people, and all their questions were on the at the end of the talk were like, oh, how do I know how do I model this, or if I should model this or not? And it's just like, I do the methodology, not the data. But what I think is for the model itself, in particular because it's quite industry focused. So we are trying to keep it accessible in terms of the modeling to industry people, mostly because we work with them as well. But I think the interesting part is that you need to ask yourself the question. This time, when you implement a fault tree, the assumptions are already there, and you don't need to make an effort to make that clear. You are not saying, I'm considering all the components independent. You're just saying, oh, the failure rate is this, and you enter in a framework. Like the assumptions, the simplified assumption are already there. I think the difference with something like what we proposed is that you need to be aware of what assumption you're introducing, because you have the capability of specifying something different. So you're saying, okay, I am assuming that the failure rate is constant, and then it's kind of your responsibility now. Oh,
okay,
hello.
Thank you. That has answered my question. Thank you, Silvia. Thank you very much for the talk.
Anyone else who's got questions or comments? Yeah, okay. So yeah, thank you very much. It's a time, so we're gonna have to finish here. But thank you again, Silvia, for coming in and give us an interesting talk. Thank you everyone for tuning in and contributing to the discussion. I hope to see you soon.
Bye.
Thank you.
Bye.
Bye.